Everybody. So I guess for this talk, it's a little bit dated. There's been some methodological developments in the last year since this paper came out. This kind of space develops quite rapidly, but the message remains the same, is that AI is not coming for your jobs. Geology is still very much needed. And there's a big gap even still marrying up all that traditional geological knowledge with all of these fancy mathy statsy type things. And they both can help each other and hopefully get us a little further in the exploration space. So before I begin, I would like to acknowledge the traditional custodians of the areas where I did a lot of field mapping. The people were extremely generous, and they have such a rich history and storytelling of the land, and I really want to acknowledge them and thank them for their generosity. The project started out one way, and plot twist, there was a big plot twist very early on. But when I began, I wanted to find out the different controls on mineralization between two roughly similar areas, because one had a lot of mineralization and the other had very little. So presumably there's some underlying obscure process or feature controlling mineralization, and I wanted to figure out what that was quantitatively. So I thought, okay, I'll chuck it all into a machine learning. Very naively thought that everything at the beginning was all well set up, and I just had to pick, which method I wanted to apply for prediction. Turns out these three systems are really hard to characterize with the existing tools. I was looking at magmatic VMS and orogenic deposits in this Archean greenstone belt region, and I was trying to look at that higher level fertility, what's controlling mineralization on a big scale. But yeah, the methodological developments at the beginning of that workflow didn't allow me to capture the things that were important for these mineral systems. So, turns out I had to spend 5 years figuring that out before I could chuck anything into a machine learning technique and get a predictive result. And I actually never even got to prediction. I wanted more as a knowledge gathering, information gathering process so that I could understand the mineral system itself by comparing these two areas quantitatively. So it follows your very typical machine learning prospectivity workflow where you pose your question, you have something you need to predict or understand, you gather your relevant data, you apply your field knowledge and your ideas of the conceptual models that go into that mineral system, and your ideas of what each data set represents. From there, you make some maps that represent things you think are important, and you have your targets and background that you're trying to train to either find or background not find. From there, you can get your results. The predictions here, like I said, I didn't look at them. I was more information gathering, so the validation or understanding after the whole process is over, that's what I spent most of my time on. So when you begin this whole process, really getting that conceptualization of your question is very important. A job well begun is a job half done, and if you don't begin well, it's going to get messy real fast. So thinking about conceptual models and the mineral system models we talk about quite a lot in papers, there's various components that are important to use to describe features of import or the processes that govern what their interactions are. Now, these are very idealized or theorized. They're ethereal, but they're in reality interpreted either through your expertise, or you're marrying up a few different data sets and your expertise, or you have some proxy that measures it. Usually that's data, kind of like geophysics or geochemistry. There's some signal you're using to represent this physical thing. So like I said, I spent most of my time actually at the very beginning of this whole process trying to make maps that are relevant for the three systems I was looking at. I wanted them to be more quantitative because quite often we use interpreted data sets early on, and there's ambiguity that gets introduced, and then compound subjectivity and bias throughout the whole thing. So when you get to your final result, it means nothing because there's so much compounded bias throughout. So I wanted to reduce that subjectivity as early as possible. I wanted to be a better reflection of geology. There's a lot of typical traditional techniques that we use for feature engineering and making maps that represent things we think are important, but they're oversimplifying geology in a vast, sometimes terrifying way that we just accept. So I wanted to see if we could do better. And then I wanted it to be more comprehensive, so look at the whole system, not just the things we like to talk about and investors like to hear about, but try and make it more encompassing, and I won't show you all of the the non-sexy ones, but the flashy ones are definitely in here. And then also I wanted to try and make it intuitive for exploration, because ultimately that's the goal. We want it to be used elsewhere and get it showtime. Coming out of all of that is information, not prediction. So looking about what is controlling that mineral system, both at each area, and how does that compare? What is that overarching, massive, here we're looking at the Superior Craton, which is extremely large, Archean Craton. What is that very much larger scale story that's going on there and controlling things? And then what does that mean at site, or even at a smaller scale at prospect level? So the two areas, I know I didn't put a picture of Canada, I'm very sorry. I used to present this in Canada and everyone knows what the Superior looks like. So anyway, this is the Superior. It's really old Archean greenstone belt, lots of rifted stuff together and then smushed again. There's greenstone belts which have been quite prospective for a long time. And it's a really good opportunity to look at these two areas because they are vastly similar. Their histories, their rock units, and so on, they're very similar, but they have such significant disparity in their endowment. Timmins is a world-famous orogenic gold mining camp. To a lesser extent, VMS, because it has the massive Kidd Creek deposit. And then there's a few small magmatic deposits. So it was a good opportunity to look at multiple systems instead of just the one. So let's make some maps. Starting out, we've got our three systems. We want to use the data science in a way, though, that respects the geology. And I think a lot of the gap that I see now is people are applying whatever the fancy method is, whatever the buzzword is, to whatever data set they have to hand. And they're not thinking long enough about what does this actually get out of your data. So I tried to find ways that could enhance that. Typically what people do, this is a very, very common data set in most prospectivity analyses, is a buffer map. Essentially, it's a Euclidean linear distance as the crow flies today. How close you are to whatever feature of interest you've mapped in your geologic bedrock map, the closer you are, the more prospective you are, and so on. But it's an oversimplification of a lot of geological concepts that are important in the mineral system and conceptual model. It's uniform along strike, how you treat the hanging wall and footwall are the same. There's a whole bunch of different things. For fold geometries, it's not looking at anything about the geometry itself, nor the orientation. There's no history embedded. Timing can be quite important, and that's all lost. So here are just a few of the ones that the maps that I've created, more in the concept space. Structural complexity, pretty important one. Lots of people talk about it. It's pretty intuitive, especially from a structural perspective. You're looking for areas where there's some complication because of deformation. So here I use auto-detected magmatic lineaments, and I chopped up all those lineaments into segments, and then measured the orientation of those segments. From there, I put a moving window across the entire map and calculated how much these segments are going to vary within that window, and that pixel gets an assignment of a variance value. If you do that for the whole map, you end up with something that looks like this. You get lots of red spaces. Those are most likely and most often fold hinges. You get shear zones where everything's been transposed. The high strain has made everything parallel, and so you get broad linear lows. And then you get fault traces, which are a bit indirect to interpret, but they're offsetting anomalies. This actually works really well in the visual space, where if you look at the different deposits and occurrences in the area for orogenic gold, they plot just outside of a peak, just outside of that fold hinge, which just kind of makes sense if you think about it. When you dig a little deeper, I think it needs to be paired with other things. It's not just, silver bullet, as we say. There's more to the story than just this representation of traps and pathways. But it's quite an upgrade from these buffer maps. You get a lot more nuanced information. You get traps and pathways embedded together, and there's a lot less subjectivity in that early stage of the workflow. Thinking about distance again, and especially about fluid pathways and distance, how close you are to a TTG that's being dewatered, how close are you to some fluid pathway coming up from deep crust, Where are some traps, perhaps, like the interior of a crystalline body? That's probably not going to have a lot of fluid flow. Things like that can be represented using graph analysis. This one's a little bit more complicated than the average technique, but in simplicity, you take a geologic map, you turn it into a bunch of nodes that define the edges of your polygons and your lines, and you assign a weight to all of those nodes. The weight represents some fluid impedance value. It's not a true value, it's just relative. So something that fluid's going to move through quite fast, you give it a low value, and something that's going to be really slow, like that crystalline body interior, is going to get a really high value or a penalty. If you add up all the pathways possible between point A and point B, all across the map, it's something that looks like this. And if you compare the two maps from buffer to this, what I call non-Euclidean distance, it's a huge improvement. You know, this is more likely what the path of the fluid would be compared to where the crow flies today. If you have a folding event that's happened after the fluids, how you measure it today is going to be quite short if you're on both limbs. But if it's pre-folding, this allows you to capture that pre-folding distance. So pseudo-restoring kind of a little bit. It's quite an endeavor to do a restoration of the structural analysis for something this complicated and this old. So this is kind of a way around it as best as I can do without spending a billion years. And this is really important, looking at all the different aspects of our conceptual model, different sources for the different things. Really, the world's your oyster on what you measure the distance to. If it's in your geologic map, you can calculate it. Geochemists are probably pretty familiar with this method. Mass change calculation's been around for a while, but it's been really hard to use in a large scale. So here I had 17,000 points of geochemistry where I had to make sense of it all in some map form. And when I started out, I realized there's actually no good tool for that. All of our exploration indices are either designed for one rock type, because you need some pre-existing rock composition to make it work, or can't be applied to more than one rock type at a time, which is an excessively cumbersome task to do if you're going to do it for each individual class of rock you have in your area. So this uses the least altered rocks, so here measured by LOI and a few other proxies, and tries to capture what the trend is, get a formula from that trend, and then you can calculate essentially the distance of your point in these charts to that average line, and that measures how much you've lost or gained based on where it falls on the line. In map form, it looks like this. A little bit blobby, I'll give you that, but it's certainly a huge improvement from just carte blanche, doing an interpolation of silica across the board, because that's just how you find your granites. You really have to do something that captures that or normalizes the underlying lithology to make it a useful tool. I have also added the stuff on the left-hand side, which is a bit of, they're squiggles, but they allow you to see the difference between, in the black, the grid distribution of pixels and their values, as well as the samples. And you can see for the CO2 and the sodium, they don't marry up that well. One is skewed and one is normal. And that distribution is really important. Not all interpolations are built the same, and they can't all be used the same way. So thinking also about chemistry and what you can do more with it, a lot of people use interpolations quite cavalierly. So this is another way to use immobile elements or element ratios that represent various aspects of, mostly here, magma chemistry, thinking about source composition and evolution and crystal contamination, things like that. Proxies for geodynamic setting, proxies for melt evolution itself. So here, I've taken an interpolation for each individual rock type in each individual assemblage and interpolated only for that package of rocks. And I did that for all of them because especially in a volcanic setting, as the melts are extruded, their sources are being evolved. You're tapping new sources, this one's being depleted, there's going to be change. And so when you just use a uniform technique across the board to do your entire map, even if you have the best proxy in the world for this, it's missing something because each rock type is going to evolve within its own package, and each package is going to be different from the next. So this really captures the usefulness of having an assemblage map that is robust. And then the last one I'm showing you here is contrast maps. So we talk a lot about traps, both chemical and rheological. Unfortunately, rheological proxies are quite thin on the ground in literature. It's getting much better for petrophysics, but a lot of engineers basically only understand granite and concrete, and they don't look at banded iron formations, and they don't look at turbidites and things like that, and publish about it anyway. So trying to get a good assessment of the geomechanical properties was a bit challenging, I'll give you that. But in any case, having those assigned to map units and then running a moving window across, trying to calculate how much the variance is within that moving window, you're able to prioritize the different contacts to find those areas of high contrast that might be zones of weakness or focal points for stress or fluid focal points, depending on the situation, the timing, and so on. For the chemistry, I used those maps you just saw before, the semi-discrete gridding, where it was masked for each rock type in each assemblage. And same thing, moving window across the board, and it gives you that prioritized set of contacts in the map area to see where things might have been, say lots of big iron change, so you're going to precipitate out of the fluids. So all of that, a little bit mathy, I'll give you that. But we can learn quite a lot from this afterwards when you start digging into it. So looking at the feature importance, so how important each map was in training the model and then in validating the model, so that it's able to, here it was trained to predict targets versus background, but it never actually got that far. I really just wanted to know how important it was in making those predictions. To even the playing field, just a quick recap on random forests. Pretend you have two plastic bags or two brown bags full of one of maps and one of data points, whether it be targets or background. You take a random handful of each, and you make a tree with it by sending a handful of points with a map. You find where that map value needs to split your data set as much as possible of targets versus background. And you do it a bunch of times with a bunch of different handful of grabs of maps, and you make a tree. You do that a bunch of times, you make a bunch of trees, which is the forest. The important thing is how often is a map able to facilitate a split between classifying a target versus background. That is the part that we are most concerned about when it comes to interpretation and validation. So if you do that a whole whack of times, I think I ran this 1,000 trees with 10,000 trees 1,000 times, so I could get a really big distribution and be confident in its result. And it allows you to see how widely spread or how stable each map is at its position of importance. So the wider it is, the more times it's varying, it's kind of waffling, and it's not really, consistent. And then as you move towards the bottom, you'll see they're quite narrow, and that's because they're quite consistently not important. But the ones at the top are, they're very wide, some of them extremely wide, with outliers even. So that's important to know because it allows you to assess, there's no metric for this. We talk about F-scores and we talk about FCC and a whole bunch of other, one single number metrics on how good a model has been trained and performs. But this is actually how you use your geological knowledge to apply validation. So there's big spread. It's interesting too to look at the three systems. Magmatic at the top, big spread. I think that's more a function of a training bias, because orogenic, where in Timmins there's a ton of orogenic data to train off of for targets and background, whereas magmatic, we had a few clustery areas to train from, but it was not as pervasive as the orogenic gold deposits. So you are getting much more variance because with every random grab from each of those bags, there's going to be some chaos, hence the random part of random forests. For orogenic, I mean, it's a good mixed bag. It's more created equal, and you get more enhanced results. Stepping through each of these individually, I won't go into all of them. This is just one example from the systems. I'll say at the beginning of this that there was quite a good match between our conceptual models published in literature and what we thought in the field with what we got out of this. Things that we expected to rank high because of experience ranked high, and things that were, we kind of knew they were not important for this type of mineral system ranked quite low. So that's great. That's a confirmation of our conceptual model for this mineral system being good. It also means our maps are decent. They do represent what we wanted them to represent. But there are always some unanticipated results, and from that we can gain new knowledge. So here, clastic sediments ranked quite high, which kind of surprised me in Timmins. But I mean, a third of the map is the Porcupine Basin, which is enormous and all seds. It's one of those lake basin types. And anyway, I think it's just biasing. It's a function of training. And if we had a bigger area that was less dominated by sedimentary units, and we had more examples of magmatic deposits to train on, I think we would have got a more robust result. Not that this is bad, but it is a flag that it could be better. Something also that came out for almost all of them, rock units that we thought were going to be really important, proximity to, for here it's ultramafic rocks, they actually ranked quite low. And it took me a few moments to think about why. It's because not all ultramafic rocks are created equal, only some are going to be winners. So you need to find the proxies that represent the ones that are going to be winners. It's a typical exploration scenario, but this allows us to see which ones do rank high and which proxies should we go after in the next data set gathering technique. If we look at all three systems together, again, this is just for Timmins, and I plotted as a ternary diagram, chopped off the corners for aesthetic purposes, but it allows us to compare what is controlling the mineral system, or at least controlling this model at the feature level. So things that plot towards the middle represent things that they all agree this is either important or not important. I'll just note both of those end members sit in the middle, but they all agree nonetheless. And assemblages sit more or less near the middle, and they ranked very highly for everybody. So I would say a good assemblage map is worth a lot. It is a hard thing to do well because it encapsulates so much information from, magma and melt source information, all the way to geodynamic setting, all the way to emplacement environments, and any post-emplacement deformation, things like that. It encapsulates so much subtle information that it's really hard to find good proxies for. So a good assemblage map, worth a lot. And then as things plot towards one end of this triangle, they become more and more important for that and less others. So the standouts are where you want to target your information, I think, if you're looking for one specific system. And then things in the middle is where you can target data sets for if you're looking for, an agnostic approach in exploration. But to the surprise of no one, orogenic deposits are related to fluid things. So fluid transport and interactions, really important. And then heat and fluid source, things like the proximity to TTGs and felsic intrusions, also very important. The two areas as well, this really allowed me to dig a little deeper into what could possibly be controlling the mineralization in one area that isn't present in another, or vice versa. If something's present and really affecting results in one area and not the other, what does that mean for our exploration scenario and understanding the system itself? So here, TTGs and LOIs, LOI is loss on ignition, and it's a representation of fluids, essentially unmapped volatiles, and then TTGs, heat sources, dewatering sources, sometimes metal sources, and so on. They're plotting on the one-to-one line, so both areas agree they're important. Standouts for these two, for Timmins, is east-west crustal deformation zones, so those big transcrustal faults that are pipelines or the plumbing system to get fluids from the lower crust up through the crust, carry metals and so on. That doesn't seem to be as important in Dryden. I will say that displays of those are important for both, but proximity to that east-west crustal deformation zone, not as important in Dryden, which I thought was quite interesting. And then proximity to basement gneisses was important for Dryden. Because basement gneisses were not mapped in Timmins, they didn't actually get a value at all, and that's why it sits on the edge. But more or less, being far away from a basement gneiss seems to be perspective, implying that being at higher crustal levels is perspective. So finding proxies for that will also be a useful technique. So that's a lot in a little bit of time. But to sum it all up, there's a whole bunch of ways you can use your geological knowledge in new ways to do more with your data and to take things a little further. If you can accept risk and represent risk or confidence, there's a lot we can do to improve. And this gap, I think, is only going to get bigger if we don't if we don't make efforts now. The technological side of the machine learning is going to far outstrip us and not be developed in a way that is actually applicable to the knowledge we have. And we'll have to backtrack and do this all again in 10 years' time. So to sum up some of the key learnings, we had feature engineered layers, so those maps, and they more or less reflected our conceptual model of the mineral systems, which means A, we did a pretty good job in representing the components in those systems, and our system models are decent. Mapping assemblages, really critical for a lot of things. It's a really good base data set you can take quite far if you do it well. For magmatic deposits, I didn't get into too much detail. Some of these summaries come from a very detailed analysis of those box and whisker plots. But more or less, mechanical characteristics seem to be quite important for magmatic deposits in Timmins. And then, to the surprise of nobody here, I'm sure, geodynamic setting, really important for VMS deposits, especially at Kid Creek. The orogenic deposits, those east-west deformation zones in Dryden, didn't seem to be too important, but proximity to TTGs and distance from the basement gneisses seem to be quite important for Dryden. So I'm wondering if that's some kind of comment on, or there's some interpretation to be made about fluid sources and timing of the plumbing connectivity in the crust while things were, hot and flowing. So thank you guys for bearing with me. That was a bit of a speed through all of that paper. If you want more information, here's my QR code. The slides will be posted, and there's QR codes throughout for the various papers associated with each method.